Great. Thank you guys so much for joining. I first wanted to get a brief glimpse of the room. Who here has already done probabilistic programming, sort of knows what that is? If you could just raise your hand. OK, great. And I assume the rest of you are probably here to learn what that is about. So it's always challenging with a talk like that. You sort of want to please both audiences and keep it interesting. So what I'm going to do is the first half of the talk is my best attempt at trying to explain that to someone with a technical background and really introduce you to what that all means and how to think about it in the right way with some very simple examples. And then basically I'm going to switch it up a little bit and do much more advanced examples. So maybe if you don't follow that last part, that's fine. If you're boring during the first part, hopefully that second part will be interesting to you. And I really enjoy giving that talk at conferences like PyData, mainly because for me, probabilistic programming is a great approach for doing statistics if you come from an engineering perspective. Because mostly the model building and the inference is all done in code. So you're not standing in front of a whiteboard all the time deriving math equations, but it's a much more engineering-driven approach. There's a disclaimer. The example that I'm going to use to motivate all this is actually not going to be just like some abstract problems, but a very concrete problem that I encountered as the data scientist at Quantopian. So I'm basically going to motivate it using that. And if you're wondering what Quantopian is, we are a algorithmic trading platform. We have over 70,000 users worldwide, and they come to the website and we have a community forum where people talk about algorithmic trading ideas and share code and everything. We have an in-browser backtester where you can write Python code to build your strategies to invest in the stock market, and we provide you with 14 years of high-quality historical data to test these strategies. You can then deploy them in the market with real money trading. We have trading competitions where you can win money. But mainly our business model is then in detecting the talent out of that pool of 70,000 users. We hope that, we know that some of those actually really know what they're doing and have a talent for this. And then actually we invest capital, outside capital, in these strategies, and we share the profits with a quant. The other two important things is the platform is completely free. Everyone can use it. So it's a great way to just have fun and explore it and maybe get started in quantitative finance if you're interested in that. But for me as a data scientist, it really becomes a problem of, well, how do we find these strategies? How do we decide whether a strategy is actually viable or not? And this is a type of plot that we look at a lot, and it's the cumulative returns of that strategy on the y-axis over time. So this is a 2-year backtest where someone built a strategy and it's buying and selling stocks, and these are the cumulative returns, and you can see basically it's just like this complete upwards line as most backtests actually look like. So in just 2 years, it's turning an 800% profit, which is absolutely amazing, right? So it's a money printing machine. What could possibly go wrong? Often though, with backtests, there's a tendency to overfit, so they often look much better than in reality than when you actually set them live. And this specific example is actually an algorithm that was submitted to one of our trading competitions. And the way that is set up is you submit a 2-year backtest, and then we let it run, in this case, for 1 month on out of sample data. So that's that very small blue line, very limited data. And then if you do well in both of those, and both of those match, then you do well in the contest, basically. So there's both of these things in, and really the big test whether something is viable or not is going to be here in the paper trading, because you couldn't have had access to that data and overfit on that data because it just hadn't happened yet. Another way to look at that problem is, instead of cumulative returns, here I'm just looking at daily returns of both of those distributions. And now it becomes maybe much more clear what the problem really is and how difficult it is your task is to decide, well, you have a lot of data of that histogram here for the backtest in blue, and it's looking pretty good, right? So you have 1% returns in a single day. That's pretty good, and that happens fairly regularly. And then you have the out-of-sample period of just 20 days. And now the question becomes, do those two sample sets come from the same distribution? And now, as a data scientist, there's multiple approaches you might take. And so I thought it might be interesting to try and compare these and just put probabilistic programming into the global landscape of what is out there in terms of like data science tools you can use. And I mean, everyone likes machine learning, right? So maybe we could do that somehow. So you have data, this black box classifier, some are more black box than others, and that spits out predictions. And actually, I mean, it already is like apparent that it's not the right tool for the job, but maybe like you train a classifier to distinguish between those two, and if it can do that, then they're from separate distributions, but it doesn't really work, right? It's not really the right framework for solving this problem. And a more general point is also that these black box machine learning algorithms are often very bad at conveying what they have learned, right? That's why the black box is, you can't really look inside that. It's like some super nonlinear thing, like, I don't know, random forest of like hundreds of decision trees. And if you are a data scientist and part of your job is to actually provide insight into your data, right, how are you going to do that with a black box tool? Moving on to frequency statistics, there you again have data, and we could run a hypothesis test, like a t-test, to say, are those two distributions different? And then we get a p-value, and that basically tells us if that is smaller than 0.05, then we say, OK, there's a significant difference. Still, there's, I think, a few number of things wrong with that approach. First of all, I call this gray box because you can look into what it's doing, but sort of there are many implicit assumptions baked into that t-test that are not like directly on the surface. One of them, which is really critical, is that your data is normal distributed. And with stock returns in general, we know that that is just not the case. So these extreme market events, like in 2008, when during the financial crisis, there were like market swings of like 10 to 20%, right? And these are really meaningful events, so you want to make sure that you capture them. But it means that your data is not normally distributed, but it's heavy tails. And mostly people use normal distributions just for the mathematical convenience, not because it's a particularly good model of reality, where often you have outlier events and you have to be robust. So already this assumption is often violated. And you might change them, but that requires rederiving all that math. And finally, the p-value, actually, often people assume that it's the probability that those two samples come from a different distribution, but that is actually completely wrong. It's a different probability, but people treat it as that, so there's a lot of misunderstanding where people have the wrong intuition about this type of test. Now, lastly, to contrast that with probabilistic programming, we have what I call a white box or open box, where you can build a custom model for the specific problem that you have. And that model is very transparent because you can just write that out in computer code and then just look at it. And the best part is, after you wrote that model in code, you can just automate the inference process. So before, with the frequency statistic, you had to do math to do the inference. Here, basically, you can run these general Markov chain Monte Carlo algorithms that give you the right answers, and they work on almost any model that you throw it at. And we are in a Bayesian framework, so we're dealing with actual probabilities. So in that case, that intuition, what is the probability that they come from the same distributions, is actually the right intuition behind that. And we can place priors to regularize and all those good things. So how can you think about Bayesian modeling in general? And for me, a very intuitive approach is to think of it in terms of building generative models that tell you how your data was generated. So we have observed data down here, and then we wonder how was that data generated, just theoretically. And often there's some latent causes that we can't observe, but that we want to infer from the data. So really, you start from the top and say, OK, these are the things that I think are driving my data and underlying it. Then you link that to the observed data by making an assumption on the distribution of that data. And that can be a normal distribution. It can be a student t-distribution if you want to have more mass in the tails and be more robust. But you can switch all that out. So that's Bayesian modeling. Now, probabilistic programming is essentially the implementation of that. Before that. So this is how you construct the model, and this is how you do inference backwards. And this is just applying Bayes' formula, which inverts that model and gives you the most likely latent causes for the data that you have observed. Probabilistic programming now automates a lot of that stack by just allowing you to write this down in code, in computer code, and PyMC3 allows you to do that in Python code. And then you just hit the inference button, and you get what is called the posterior, the most likely values of your parameters given the data. So now to come back to the problem that we had initially, we wanted to know, do those returns come from different distributions? So we want to model these returns. And this is what that would look like. So down here, again, we have our observed data, that's the daily returns. And here, I'm not going to say that it's a normal distribution, which we know to be wrong, but actually a student t distribution, which is different in the way that it has a third parameter that allows you to create more mass in the tails. So more extreme events just are more likely. So it's a very nice distribution to use in reality just because it's much more robust than a normal distribution would be. So instead of 2 parameters for the normal distribution, the location or the mean and the scale or the standard deviation in the case of the normal, we have a third parameter that controls the mass and the tail. So these are my parameters or the latent causes that I want to infer given the data. And again, inference then works backwards. And this is what the model would look like in PyMC3. And it's not the best model that I'm building here, but it's, I think, the most illustrative model. So every program will look fairly similar. So here I'm just importing everything to be lazy. And then there's this with context. And that's more of a technicality. You don't really have to worry about that. But essentially, it means that everything that happens indented under here will be tied to this model object. And that basically is a way to keep all the things that you create below that to a common thing. But it's boilerplate code. Every model will have that. The more interesting part is now I can define these latent causes, my parameters of the model. Right? So these are the 3 ones that I have. And because we're in a Bayesian setting, we have to place priors, which are my beliefs about these parameter values without having seen any data. And in this case, I'm just going to say, and that is a subjective choice that you can make as a modeler, and it gives you a lot of freedom and power to actually inform your analyses, because often you do have prior information going in. For example, the location or the mean returns of the strategy, we already know to be close to 0, right? I mean, it's not going to be 100% daily average returns. That's ridiculous. And it's not going to be minus 20, hopefully. So in reality, I might place a normal distribution around that. But here, I'm just going to say, OK, it's a uniform distribution with assigning equal probability to all different parameter values in this range. From minus 100% to 100%, scale can only be positive. So I'm setting the lower bound to 0. And the tail parameter can also only be positive, so I'm saying that is 1 to 10. But as I said, you can and you should use different priors than these just to be more informative. So uniform is like a often used distribution if you sort of want to be uninformative, but actually it often pays off to be informative and inform the model of what you think is going on. Now, the second part is how do we tie that to data? And as I said, we're using a t-distribution. And by the way, the first argument is just the name. You can name the random variables. And here we pass in the data. So that will just be a NumPy array. And here we're using the observed keyword, which tells it actually that this is used to infer these other parameters. Go ahead.
Does it support improper priors?
Yes, you can also use improper priors. Yep. And this is where you tie together basically these parameters with the data via the distribution function. So when I execute that in Python, actually not all that much happens. So under the hood, just a technical note, we're using Theano, if you know what that is, to build up a compute graph out of all these probability distributions. And on that, we can compile that to C behind the scenes. And that means it's fast. It's just in time compiled. We can compute gradients. So Theano is really powerful as a framework behind all of this. But you're not really exposed to that when using PyMC3. So that's why I just mentioned that in passing. But critically, no inference is going on yet. So we just built the model. And now the question is, well, how do we solve all that math, right? So there's like this whole thing going on that you have to compute. But as I said, you can do that automatically and model specification and then turn to inference. And that is really simple because we just have to instantiate a Markov chain Monte Carlo sampler. And what has really given this field a huge boost is this new class of samplers called Hamiltonian Monte Carlo, and NUTS is one of those. And those really work much better on extremely complex models. And PyMC3, that's the main reason actually why we wrote PyMC3, is to be able to use this new class of samplers. And then you just draw 5,000 samples, and that will just basically turn the Bayesian crank and solve what we've given it. And next we can look at the answers that we care about, right? So, and we can plot these so-called posterior distributions. And what is really important now is that these are not the returns that I'm plotting here, right? That's my belief in the mean returns. So that's just one parameter of my model. And you can just compute the mean over the input array that I passed in, right? And you get back a single number. But that number does not tell you anything about the confidence in that number, right? So with more data, it would be more accurate, but you have no way of knowing how accurate that is, right? So here, we're not dealing with single numbers, never. We're dealing with distributions over possible values of parameters. And that is encoded in that width of that distribution. So intuitively, you can think, OK, in my in-sample set, we have lots of data. I have a lot of confidence. So the possible mean returns parameters, values that I can get, or that I would deem likely, given my model, is very narrow. So I have lots of confidence. I know, OK, this is the value. It's very close to this one. Now, with the out-of-sample set, we have very little data, so we can't really say anything. And that naturally comes out of the model by just giving me a wider posterior distribution. And if I had no data at all, basically, then it would just be the prior, where I just say, well, it's going to be uniform everywhere. And over time, basically, it will like go tighter and tighter around the region that is the true parameter.
Sorry, in your example, you had uniform and student.
Yeah, so the priors are uniform distribution. So there I'm just saying everything, without having seen the data, everything is going to be equally likely. But then there's a different thing, which is the likelihood function, which is just how do I think my data are distributed. And that, I say, is a student t distribution. So it's the shape of the data and my knowledge about the parameters. But now what is cool about this is that once we have it in this framework, we can very easily ask statistically meaningful questions about that. And if you remember, the main question was, well, do those two agree? Do they come from the same distribution? And I can now ask, what is the probability that the mean returns of my in-sample strategy are below my mean returns in the out-of-sample? And I get back a number that is like a hard probability number. So that is the probability that we care about, right? And so 3.34%. So a Bayesian test that I just created out of nothing, basically, tells me that these two are likely to come from a different distribution with a different mean. So I might not want to invest in that strategy. I'm going to skip this, but you can also basically make predictions with that. But I'm going to show that in more detail later. But before moving on to the next part, I wanted to basically tell you what actually happened, because we got to learn that. Before we had these tools, we had different ways of like comparing the two periods. And because that strategy had such an amazing backtest and the forward, the paper trading was still sort of OK, it actually won the contest. And we deployed $100,000 to it and let it sit in the market for 6 months. OK, so who here thinks knows what happened? This is what happened. So with these tools, basically, we could have already earlier been alerted to the fact that actually something did not seem to match up with how good the backtest was promising the strategy to be. And yes, I mean, the most likely thing what had happened is that the quant developing the strategy just overfit on past data, and that happens all the time. So it's really important to discover that. OK, so that is the introductory part. So yeah, maybe 2 quick questions for understanding purposes.
Why do you compare the probabilities to see to decide if it's different, as opposed to do like a KLB divergence to see if a global measure of the density is different?
Well, I mean, you mean just a different way of comparing the posteriors?
Yeah, like you do like a cross entropy, so you look at like
Ah.
the entire probability of
Yeah.
one versus the log of the ratio of the probabilities,
Right.
so that you have actually comparison of the density, as opposed to just a slice.
Yeah, you can do that too. And I think actually that would give you a similar answer, but it's sort of a distance metric, so it's not a probability that you get.
No, it's a distance metric.
Yeah. So
Information.
yeah, you can do that. For me, thinking in terms of probabilities is more intuitive, so that's why I use that. Last question. I understand. Yeah. Yep. So the question is, with only 25 days of data, what can you really say? Shouldn't you have to wait more? And the answer is it depends, right? I mean, if the returns that you're getting are like super poor and like it like tanks immediately, then like you don't need to wait 6 months to know that, right? And that is, and in this case, actually, we didn't have to wait for much longer. Like already here now, we reached a level of significance where we might be confident. We might still decide to deploy it, right? I mean, it's just an information that we provide. It's not making the decision for you, but now you basically know what risk you're taking on when making these decisions. Okay, I'll take more questions at the end, but I want to get to the advanced example. Okay, if you present a PyData, you have to have a IPython notebook. So yeah, this is a fun little model I built to like sort of counter the deep learning track that's going on in the other room so that you guys don't miss out. So I built a Bayesian neural network, and I'm going to go over that fairly quickly and use like a lot of the lingo, just assuming that those people who know will understand it. But what I did is I just created these 2 distributions using scikit-learn. You can generate all kinds of data sets. And the key thing is, well, it's 2 classes, binary classification, and they are not linearly separable, right? So a sigmoidal, logistic regression would just like fit it through here, but it wouldn't really solve the task in a satisfying way. Let me increase the size a little bit. So instead, what I'm doing is I'm building a Bayesian neural network, and I have my data X train and Y train, so I use a train and a test set. And I want to, of course, train the model on the trained data, and then later I want to make predictions, so I have to switch out that data of the model. And this is now Theano stuff where I have to create a shared variable for my in and outputs, so that I can later change the values in here when I want to make other predictions. I'm going to use 5 hidden neurons. Here I'm just creating initialization for the weights of my neural network. And this is what the model looks like in PyMC3, so we again have that boilerplate. And here I'm defining priors, so these are my latent causes, right, for the weights from the input to the first layer, from the first layer to the second layer, from the second layer to the output layer. Output neuron is just a single one. And I'm just going to place normal priors on these, centered around 0 with a standard deviation of 1. And I'm using the shape because now we're doing matrix algebra. So I can just define the whole thing. And test val means this is what I'm going to initialize it with. OK, now I have set up the my parameters, the priors on my model. Now I just have to build that neural network. And all that is really is just applying the dot product matrix multiplication between my input and the weights of the first one. Then you apply the nonlinearity. And here I'm using a 10H. You could use a sigmoid, but actually 10H works better, I found, in this case. That's the activation of the first layer. Then I just multiply that with the activations of the second layer. And then I compute the weights for the output just like that. So this is just like the boilerplate logic of like a very simple neural network. OK. And then my data, in this case, is a Bernoulli. So that means it's binary with just zeros and ones. Those are the labels that I want to predict. And I pass, so this is what I'm passing in here. This is the output data. And then act out is just the activation of the probability estimate of the labels of all of these. And then here I'm using a metropolis sampler, which actually works fairly well in this model, even though it's quite complex, actually. And as you can see, it's 14.5 seconds. It's for 10,000 samples. That's pretty good, but not all that fast. So as I mentioned already, these samplers tend to be a little bit slow, and that is one of the biggest problems, I think, of when you want to really use that. And now I want to predict on the holdout set. So as I already mentioned, I'm going to change the values from the train to the test. Now these will be changed in the model, and I call sample PPC, which is a posterior predictive check. Essentially, I'm generating new data from my model, given the parameters I estimated. And the key thing is that my predictions actually now will not be just the best fitting values, but actually will be sampled taking the whole posterior into account. So we'll also get uncertainty in my predictions. That's something that you can't get otherwise. And here I'm plotting the predictions on the holdout set, and you can see that it's matching pretty well. And moreover, sorry, I'm going to try. So we had 95.4% accuracy, whatever that means. But what is more interesting is we can now also map out the whole space. So basically try and create predictions for every point in the space, and then plot that. And this is what that looks like. So now we basically know the color here is the probability that that point with that coordinate will belong to class 1 or class 2. And you can see, OK, like as you would expect, this is basically what the hyperplane looks like that goes through here. And then we have, so far that is everything you could have done with just plain neural networks, right? So we haven't really made use of the fact that we're using Bayesian statistics other than that we get uncertainty in these parameters. But something that you can't do otherwise is now, as I mentioned, get uncertainty in your predictions, right? And I can just plot the variance of that space that is getting predicted. And it's looking as you might assume, right? So we're very confident in answers over here. But as we get closer to that boundary, our uncertainty in these predictions increases. And that's really powerful if you imagine in practice, if you want to make real world decisions, right? I mean, if you train a model to predict whether someone has cancer or not, right, you better tell them the uncertainty in that prediction, right? And not just like yes or no. So that, I think, is really a very nice property and shows you that it's not that like there's probabilistic programming and machine learning, but actually a lot of the machine learning community is using the Bayesian framework to express their models and build them. As I said, it's really slow. Well, I mean, these samplers have gotten a lot faster, but still, if you want to be really fast, sampling is not going to be the way to go. And fortunately, there is a different style, which is called variational inference, where you can, instead of sampling from that distribution, you fit a distribution to your posterior by making some assumptions like that your posterior is going to be normal. And one really cool recent paper that came out from the STAN team is called ADVI, Automatic Differential Variational Inference. And that just allows you also, on like whatever model you dream up, do variational inference on that, and it's going to be really fast. And we just recently included that in PyMC3, so I'm really excited about that. And this shows you how to run that. So again, now we're switching here back to the train data because we want to retrain the model. And I'm just calling variational ADVI instead of instantiating the sampler. I tell it, OK, run 2,000 samples. And then it's going to be very, very fast. And this is basically the elbow, the evidence lower bound. It doesn't really matter, but it's basically the objective function. So you can see how over time you optimize to a stable estimate. And basically then at the end of that optimization, so it's not sampling, it's optimization now, you get like your posteriors. And that will be the mean and standard deviation parameter that you also got to return. OK. And I can do even one better, which is you can use ADVI using mini batches as well. So the problem also with Bayesian statistic is that to evaluate just a single point, you need to compute the likelihood over all your data points. So for deep learning, for example, right, you just like pass in training data once and then optimize, and then basically you're done. With Bayesian statistics, you have to evaluate the same data over and over again. So that's got to be extremely costly. But actually, with ADVI, you can also use mini batches, which is the subsets of your data. And that way, you can scale to arbitrary sizes almost by just using subsets, but still getting the correct answers in the end. And that was provided recently by Taka Yoshioka, who did the work of including that in PyMC3. So I'm giving it a shout out here. I just have to like redo the model, and this is what that looks like. We're not like completely set on the API, but I think this is pretty well. The key point is that we're creating a generator that will provide me subsets of the data. So I'm just using 100 data points at a time, and then I'm passing that to the ADVI mini batch function with like which variables should be like replaced. It's not difficult to like set up, but in any case, it works, and it's going to be even faster, right? So like now we could use millions of data points because we're only going to look at 100 at a time. And also within here, you can imagine, because this is just a generator, you don't even have to hold this in memory, right? You can just pull from a database inside that generator and just provide the most recent data to your PyMC3 model. This is just to show that, yeah, we also converge even faster, actually, to the correct answer. So that was the advanced example. And I just want to close with this overview slide of comparing the different approaches. So as I showed you, hopefully, probabilistic programming, you can also do prediction, right? We can use a neural network model, can predict returns. The key thing really, though, is I think it's a great tool, and that's mostly what I use it for, is actually gaining insight into the data, building models, being very quick to reiterate these models, change them, see what the data tells me, just learn about your data. It can track uncertainty in a much more principled way than frequentist statistics. And the assumptions on your data are laid out in your probabilistic programming, right? So if I tell you, like, this is the model I use, you can immediately critique it and say, like, oh, that is terrible prior or something. Or like, I would do that differently, and then you can change around it and play it. So that is for me, a key point. And the model construction happens in code, right? It's just Python code. And we have these very general inference algorithms. And hopefully with like this new style of inference algorithm with ADVI, we can also solve the speed and scalability issues that basically have been one of the downsides here. But I still left it as Mark. Next time, hopefully I'll convert that to a check. This is just a whole bunch of links that you can look up later. But with that, I'd like to thank you for your attention. Any questions? Ole?
You switched in the ADVI, you switched from student T to Gaussian.
Yep. I think you misread. The model is actually the same. There was a different reason why I had to just replace that. It's using normal priors in both cases. And you're right that like these variational inference algorithms used to not be general at all because you needed to derive the update equations, and those were specific to the model. So you're back to your frequencies problem. This ADVI does not require you to do that. It just like works on whatever. It doesn't have to be conjugate. It can't be discrete, but yeah, it can be any continuous model that you want. It can be hierarchical and everything.
I've tried to sort of learn up on Bayesian statistics and modelling. A lot of the resources I see are on PyMC2. Can you quickly give a rundown of the difference? And I presume the concepts are the same, but the programming is going to be different. So can you give a quick rundown on the difference between the two?
Yes. So I didn't mean to do that. Yes. Oh, sorry. Most of the documentation that you find is going to be for PyMC2. So what are the resources for PyMC3? And I think probably the best place to start is, it's still a weak spot, but, well, there we go. But the website has a tab with like examples, and there's like some really cool, simple and more complex models that are all PyMC3, and it actually is not just like PyMC3, but it's also just learning to model and explaining like the different models. So I think that's a good way to start. Another great place to start is this is KMDP's book. That is still PyMC2, but we're working on changing that to PyMC3. If you want to help out with that, please get in touch. But this book actually is really well written. It's the puppy book because it has all these puppies on the cover. So not only do you get cute puppies, but also great introduction, and someone has done the work of converting all of that to PyMC3, all the examples. So you can find the link on the PyMC3 repo and basically go through the book, but read read the PyMC3 version of the book. And that's probably the best way if you say, okay, I want to get started. I don't really know the statistics and behind that in a principled way. That is what I most recommend doing.
No one's done a Rosetta Stone side-by-side comparison. This is how you do it in PyMC2. This is how you do it in PyMC3.
No, but now that you say it, actually, it's a really good idea. Yeah. Any more questions, please?
Is variational inference approximation mean field?
Yes.
So when you have a neural network, all weights are assumed to be independent.
Yep. Yep. So the question was the variational inference, whether that is a mean field approximation where you assume that where you ignore the correlations in your parameters. And one of the nice properties of Bayesian statistics and MC sampling is that you do get the correlations in your parameters, something that will screw you up if you do maximum likelihood estimation. But these variational inference algorithms ignore the correlations and just try to fit a uniform Gaussian to that high-dimensional posterior using a normal distribution in the transformed space. And there is actually a previous version of that paper showed that you can also do estimation of the correlations. It just becomes a more difficult optimization problem, but it exists, but it's not implemented.
Okay. So let's thank Thomas again.
Thanks. And just want to, directly after me, John Cedar is going to talk much more about that hierarchical modeling, which is a great, powerful tool as well. So definitely stick around for that for more Bayesian goodness.